Earthquakes. The very word evokes images of destruction and chaos. Simply put, an earthquake is the shaking of the Earth's surface. This shaking is caused by movements deep within our planet. Imagine a giant jigsaw puzzle, but instead of cardboard pieces, we have massive slabs of rock called tectonic plates. These plates are in constant, albeit very slow, motion. Sometimes these plates get stuck as they grind against each other. Pressure builds up over time. Eventually, the pressure becomes too much and the plates slip. This sudden release of energy sends shockwaves through the Earth, resulting in an earthquake. The point where the earthquake originates below the Earth's surface is called the hypocenter. Directly above it, on the surface, lies the epicenter, usually the area that experiences the most intense shaking. To grasp the science behind earthquakes, we must delve into the world of plate tectonics. Imagine the Earth's outermost layer, the lithosphere, as a collection of massive tectonic plates. These plates are constantly on the move, driven by the heat from the Earth's core. Think of a pot of boiling water. The heat causes the water at the bottom to rise, cool, and sink again, creating a continuous cycle. Similarly, heat within the Earth's mantle creates convection currents that push and pull on the tectonic plates above. This movement gives rise to continents, mountains, and earthquakes. There are three main types of plate boundaries, each associated with different types of earthquakes. Convergent boundaries are where plates collide, forming mountain ranges or subduction zones. Subduction zones are responsible for some of the most powerful earthquakes ever recorded. Divergent boundaries are where plates move apart, creating new crust at mid-ocean ridges. Transform boundaries are where plates slide horizontally past each other. The San Andreas Fault in California is a prime example of a transform boundary. These boundaries are known for producing frequent, often shallow earthquakes. When an earthquake occurs, it releases energy in the form of seismic waves that travel through the Earth. These waves cause the ground to shake, sometimes with devastating effects. Understanding the different types of seismic waves is crucial for understanding how earthquakes are measured and how they impact structures. The fastest seismic waves are called primary waves or P waves. These waves travel through both solid rock and liquids, compressing and expanding the material they pass through. Think of a slinky being pushed and pulled along its length. That's similar to how P waves move. Next come the secondary waves, or S waves. Unlike P waves, S waves can only travel through solid rock. They move the ground up and down or side to side, perpendicular to the direction the wave is traveling. Both P waves and S waves travel through the Earth's interior. However, earthquakes also generate surface waves, which travel along the Earth's surface and are often the most destructive. We often hear about earthquakes being measured on the Richter scale. However, scientists now primarily use the moment magnitude scale to quantify an earthquake's power. The moment magnitude scale measures the total energy released by an earthquake. This scale is logarithmic, meaning each whole number increase represents a 10-fold increase in wave amplitude and a 32-fold increase in energy release. An earthquake with a magnitude of 5.0 releases about 32 times more energy than an earthquake with a magnitude of 4.0. The largest earthquake ever recorded, the 1960 Valdivia earthquake in Chile, had a moment magnitude of 9.5. Measuring an earthquake's power is not just about magnitude, we also need to consider its intensity. The modified Mercalli intensity scale measures earthquake intensity based on observed effects, such as damage to buildings and the movement of objects. The intensity of shaking depends on factors like distance from the epicenter and local soil conditions. While we cannot predict earthquakes with pinpoint accuracy, we can take steps to prepare for them and minimize their impact. Earthquake preparedness involves both individual and community-level efforts. On a personal level, it's crucial to have a plan, including knowing safe spots in your home to take cover and having an emergency kit. This kit should include essentials like water, non-perishable food, a first aid kit, a flashlight, and a battery-powered radio. Securing heavy objects in your home is essential to prevent them from toppling over during an earthquake. Knowing how to turn off your gas and water supply can prevent further damage in the event of leaks. Beyond individual preparedness, building codes play a vital role in mitigating earthquake risks. Structures in earthquake-prone areas are often designed to withstand ground shaking, incorporating features like base isolation systems and reinforced concrete. Early warning systems use networks of sensors to detect the initial P waves of an earthquake, providing seconds to minutes of warning before the strongest shaking arrives.